The bell-shaped curve, the classic distribution. Now, it's surprising how often this pattern appears. So when we're collecting our data and we draw up a histogram, we often find this sort of pattern where it goes up and then it comes back down again. We find that the mode, or modal class in this case, is somewhere in the middle of the data. Distribution is almost symmetrical. I mean, that's obviously not symmetrical, but it's got that going up, going down feel to it. It's almost symmetrical. In a true symmetrical one, so a classic typical bell-shaped curve, then all three of the mean, median, mode will be the same. Because remember, these are measures of central tendency, and so if we've got this symmetric shape, then all of the centers sort of merge, if you like. So the median and the mode and the mean would always be the same. Whilst the data, certainly in the example I've got there, is not symmetrical, when we're dealing with real data, it's amazing how often it's almost symmetrical. It's got that same pattern. And the other thing that happens in a bell-shaped curve is it tails off very quickly at either end. So it comes down and then just tails off. Which brings us to the normal distribution. Now, a random variable who has this probability density function is the normal distribution. It's quite a formula there. 1 over sigma, which of course is standard deviation, times the square root of 2 pi e to the power of minus x minus mu, the expected value or mean, squared over 2 times the variance. That is our normal distribution. And when we want to describe data as normally distributed, this is how we would say it. We say the random variable x is distributed, so we say, well, we put a tilde there, n representing normal distribution, and the two key pieces of information, so the mean and the variance, or the expected value and the variance. So characteristics of it, there it is, the classic bell-shaped normal distribution. It's an even function. Well, it's symmetric. So function x equals function negative x. The maximum value is the mean. In other words, the mode is the same as the mean, which, as I said before, also happens to be the same as the median as well. Thus, these two together are telling me it's symmetric about that mean. And here's an interesting one. It inflects one deviation away from the mean, either side. That's where the point of inflection can be found. Now, so that's any normal distribution. When we standardize data, we like to go to the standard normal distribution. And that's the one where the mean is 0 and the variance is 1. Z, that's why we often call them Z-scores. So Z is distributed, normal distribution, 0 and 1 are our two key pieces of information. And this becomes the formula. 1 on root 2 pi e to the power of minus z squared on 2. There's our probability density function. How do we calculate the probabilities? Remember, our cumulative function then would become the integral of that function going from minus infinity up to z. Notice we use the lowercase for the density function, uppercase for the cumulative frequency. It's the cumulative distribution function. And there's a graph of that cumulative distribution function. Actually integrating that. Here's the bad news. With what we've looked at in our range of functions that we've looked at for integration and all our techniques, we can't do it. But that's not a big deal, because we're not actually interested in the function itself, because we're going to be finding definite integrals and we're just interested in the answer, the value. And we can estimate that using a trapezoidal rule. Don't panic, you don't have to. Okay. But as we're always going to go back to the standard one, we just have a table of values which we can read off and get the answer. Something like this. A whole heap of different values. And so if I want to find the probability of z being less than or equal to 0.25, so the area going from minus infinity up to 0.25, I just look in my table and go, okay, 0.2 and 0.05, where do they intersect? Oh, there's my answer, 0.5987. Now we just read off the table. We don't actually have to do any integration to find the value. So how do we then use that table? Obviously, to find a particular one, we'll find the intersection of those 2 points. But often they'll only give us a table of values for the positive numbers. And it could be negative as well. So all right, if I want to find the probability of z being less than or equal to a particular value, I'll just look at that table and read off z, whatever score it is. But if it's a negative number and that's not in our table, hey, this is going to be the same as 1 minus that. If I want to work out whether it's greater than or equal to, then that would be minus z, again because of the symmetry. And then we could work out minus z by going 1 minus and reading off the z. Most of the time we're going to be going between two particular values. All right, we just read off z2 when we subtract whatever z1 is. And if we are looking at symmetry and we want to find the absolute value is in between, in other words z's going between minus z and z, then it turns out to be 2 times z minus 1. Your calculators of course can do this as well rather than reading off the tables. Now in the HSC, which has got to be what's called a technology neutral paper, you can't assume you have particular types of calculators and things like that. They'll often give you a table of values, and so using this table of values, go and do it. Right, on your calculator, if you've got the 100 AU, who's still using a 100 AU? Anyone? Mode 3, well you should know that one, that puts it into statistics mode. Then when you go shift 1 5, that should bring up your standard normal distribution menu, and it's got 3 options, P, Q and R. That's what each of them are representing. P is phi z, so going from minus infinity up to, well they've used t here, up t. Q is just going from the mean up to t, and R I guess is the opposite to P. So it's the missing bit. It's going T up to infinity. So P is the one you'll be using most of the time on that one. So if I wanted to find 0.25, I'd select 1. That would get me the P option, and I'd just simply type in, well, 0.25, that's what I want to find, and it should come up with the answer. Well, the calculator gives you a few more decimal points than the table, but 0.59871. For those that have the 8200, is that the new one? That's the new one, isn't it? Yeah. 82. So how many people have got the wonderful new one that makes life easier for yourself? Oh, okay. Here's how you do it on the one that makes it easier for yourself. Ready? Okay, on the home screen, choose the distribution menu. Then select normal CD, because you're saying I want the normal cumulative distribution. Then you need to tell it what the lower end of the data is. Now of course you can't enter in negative infinity, so just put in a really big number like -1 times 10 to the 99, so that's really small. But then you have to tell it the upper end, that's the one you want to find, so 0.25. Then you type in the mean, but I'm pretty sure it's there by default, the normal one, so 0 should already be there. And similar with the, notice, deviation, not the variance. Okay, so you put in the standard deviation, not the variance. And again, that should be there by default for that one. And then execute, and it should go and find it, and it gives you a stack of decimal places for that one. Isn't it so much easier than this wonderful new calculator? But look, the reality is the table of values is probably going to be the quickest way of doing it. Okay, so if we had to find z less than or equal to 0.44, we'd get 0.67003, or of course if you put in the calculator you'd get that. If I wanted to do minus 0.81, then I'd say, oh, that's the same as 1 minus 0.81, and I'd look up 0.81 and get that. Of course, if you're using a calculator, you could type in the minus 0.81 and it would come up with the answer straight away. If I wanted to go between two values, then I'd have to look up 0.94, but then for the negative 2.34, I'd look up 2.34 and subtract that from 1, then subtract that from 0.94, or again, you could just plug that into the calculator. Absolute value one, so going in between minus 1.15 and 1.15, well that was 2 times, look up the 1.15, subtract the 1. Now, the other way they might phrase a question is they'll pick particular numbers, and you can just use that empirical rule. And that's on the reference sheet too, by the way. You don't have to remember the percentages between each one. And so often the data conveniently happens to be, one deviation away from the mean and things like that. So we can say, well, we know what percentage it would be. Okay? So in a normal distribution, we know 68% of the data lie, or one deviation either side of the mean. We know 95% two deviations either side of the mean, and virtually all of the data is 3, so 99.7% of the data lies between 3 deviations from the mean. So that's the other way, as I say, they might phrase questions so that you can just go, I know it's 2 deviations from the mean, therefore the probability is this. Okay, so 16D.